All right, so next up we have concentration units, 13.4. So this will be a pretty short description. We mostly need to just go through the different formulas that we have. Starting with just simple percent by mass. So if we're figuring out the percentage of a solute, say A, it would be the mass of that solute in solution divided by the total mass of the solution times 100. So that's pretty basic. Parts per million and parts per billion, oftentimes we see this in different environmental applications. For instance, the amount of lead in groundwater or soil samples, because they're in very small amounts, and the amounts are actually more potentially a problem in those smaller amounts. So it's similar to the concentration units, where you got the mass of the solute divided by the total mass of the solution, but instead of multiplying times 100, parts per million has you multiplying by 1,000,000, parts per billion multiplying by 1,000,000,000. All right, and then we have the mole fraction, which we actually talked about when we did the gases. So the mole fraction of A would be the moles of A divided by the total moles in solution. Okay, so this is, I'm going to kind of set us apart because we not only need to know the number of moles of the solute, but the moles of the solvent as well. Our old friend molarity, moles of solute over liters of solution. And then one that's very similar to that, molality. Notice the difference in the units here. We've got capital M for molarity, small m for molality. And molality is moles of solute per kilogram of solvent. Notice the difference between the molarity is liters of solution, molality, kilograms of solvent. One of the things we'll talk about in class is, why would we need that secondary unit? What's the advantage? So you might want to think about, obviously it's the denominator, the liters of solution versus kilograms of solvent that make the concentration units different. So you might think about why we would use those. So here's a typical problem that we'd have to deal with. Actually maybe a more complicated problem, but we've got muriatic acid is used to lower the pH of pools as well as to clean several different surfaces such as marble, slate, brick. The active ingredient is hydrochloric acid, and the bottle states that the solution is 30.2% HCl by mass. Assuming the density of the solution is actually it should be 1.31 grams per milliliter, determine both the molarity and molality of the HCl solution. So we'd start off with the formulas for these. So if we go with the molarity first, molarity is going to be equal to the moles of HCl divided by the liters of solution. Now, we aren't given any amounts of this, but we are given the percentage. So, given the percentage, what we're going to do is assume we have 100 grams of this solution. So if we have 100 grams of this solution, then we would have 30.2 grams of HCl and 69.8 grams of the water. Now we'll use that later on in a calculation. The 30.2 grams of HCl we can use to get the moles of HCl. So the 39 CHCl, we've got 36.5 grams of HCl to 1 mole of HCl. So that gives us 0.827 moles of HCl. Sorry about my marker. The board seems to be jiggling a little bit. So there's our moles of HCl. Then to figure out the liters of solution, And let's do that right below here, maybe in green. To figure out the liters of solution, we'll use the density. So you got 100 grams of solution times 1.31 grams of solution to 1 milliliter, and 1,000 milliliters to 1 liter, which then gives us a volume for our solution of 0.0766 liters. Now again, this is just the our kind of assumed upon 100 grams of solution. Obviously, you can have different volumes of the solution. Now, if we go back over to our problem, we plug in the values that we found. We have our 0.827 moles of HCl. We have our volume, 0.0766 liters, which results then in a molarity of 10.8 molar. Okay. So we basically took the data that was provided, determined the number of moles of HCl, used the mass of the same solution and the density to figure out the volume in liters, and then just plugged it into our formula. Now, our molality, let's go ahead and do that in black. I've already done a lot of the work for that. Again, we've got moles of HCl. This time we've got kilograms of our solvent, which is going to be the water. So our moles of HCl, 0.827 moles. Our kilograms of solvent, so we had, where was our mass of water? Right up here. So we had 69.8 grams of HCl, or H2O, which is our solvent. And we need kilograms, so 1,000 grams to 1 kilogram gives us 0.0698 kilograms of water for the solvent, which then gives us a molality of 11.8 molal. Okay. So you can see the molality ends up being a little bit higher than the molarity due to the fact that when you add the solute to the solvent, the volume is going to get slightly larger. So again, one of the things you're going to want to do, so we'll do a bunch of practice on these in class. One of the things you still want to do a little bit of thinking about tonight, in addition to doing the problems, is why we have a need for both of these concentration units, molarity as well as molality. What advantage would one have over the other?